Good morning, grade 11s. Welcome to, what day is it? Wednesday, May the 27th. And we just want to begin with going over curved mirrors. I know there were at least one question off of yesterday's assignment, and I'll do that toward the end of the video. But for now, we want to talk about some curved mirrors, concave and convex mirrors. You can kind of see the board behind me already. But before we get started on that, we want to start with our verse of the day today. Today's verse comes from Psalms 63. It's actually 4 verses. We're going to read Psalm 63 verses 2 to 5, where it says, I have seen you in the sanctuary and beheld your glory, your power and your glory. Because your love is better than life, my lips will glorify you. I will praise you as long as I live, and in your name I will lift up my hands. I will be fully satisfied with the richest foods. With singing lips, my mouth will praise you. So continue to praise our Lord and Savior. Behold his power and glory as you go throughout the day today. All right, let's talk about curved mirrors. So when we talk about curved mirrors, we're talking about concave mirrors and convex mirrors. Now, you will have to remember the difference between them. And so I've drawn some diagrams here, and I've got a bunch of stuff on the board. We'll go through it all. And again, you can rewatch this video as many times as you need to in order to understand which is which and what are the parts are that we need to worry ourselves with. So here I've got a concave mirror. Now, concave mirrors are also called converging mirrors, and we'll see why in a moment. The concave mirror is, again, it's a circular mirror, a spherical mirror, with the reflecting side on the inside of it. All right, so concave, you can think of it as a cave. When you curve a mirror, it looks a bit of a cave into it. That's a reference to a Bill Nye video. If you ever want to watch a good Bill Nye video, you can watch the one on light optics. All right, so we have a concave mirror, which means that the reflecting surface is on the inside, and it means that the light rays will come in and converge to a point. All right, so that's why it's called a converging mirror at times. And we'll talk about the rules for these light rays in a moment. Over here we have a convex mirror or a diverging mirror. And again, same spherical mirror, but now the reflecting side is on the outside of the circle. And what happens here is the rays come in and they get reflected again away, but those reflected rays diverge from one another. To diverge means to get further and further apart. All right, so that's the simple difference between them. On a concave mirror, again, they're both spherical mirrors, but in a concave mirror, the reflecting surface is on the inside of the circle, whereas on a convex mirror, it's on the outside of the circle. Now, with this, there's a number of parts that we have to be aware of and a number of terms that we have to be aware of. And so I've drawn this red line that goes through the middle of our scenario here, and so our concave mirror is sitting on this axis, and it goes through the middle. So there's a couple of points here. This line is called the principal axis. All right, and we're going to shorten that to PA because we don't want to say principal axis or write principal axis every time. So we're going to shorten it to PA. All right, and then we have a few other points here. This point here, where the reflected rays are going through, is called the focal point. And so we'll call that F for focal point. And then this circle would also have a radius, right? And so somewhere here, and it doesn't matter where it is, it can be the same on the focal point, it can be inside the focal point, it can be outside the focal point, it can be anywhere. Well, it won't actually be inside, the focal point will always be inside. And so the circle center would be here, and we would call that C for the center of curvature. Okay, where's the center of this circle? And again, that distance from the mirror to the center is called our radius. And then there is a relationship between the radius and the focal point, and that is what I've put in the box here. There's always a common relationship when you have a spherical mirror, that the focal length, the distance from the mirror to the focal point, okay, so this is focal length, is equal to the radius divided by 2. So it's always going to be half. Okay, and this is for spherical mirrors. If your mirror is a parabola or some other shape, this rule obviously won't hold. This is for circular mirrors. And so the focal length is the radius divided by 2. All right. The same thing happens over here on this diagram. Again, we've got our red line going through the middle. That would be our principal axis. But now our focal point is on the back side of the mirror. What you would notice is that these, just like when we were doing plane mirrors, the reflected rays get projected behind the mirror. Same thing happens here. Here's a reflected ray. It is going to get reflected in behind the mirror, and it too will go through the focal point. Okay, and so that's how the rays work, whether they get reflected inside into a focal point or behind the mirror towards the focal point. They always go through the focal point. Now, we're just going to move over to a demonstration. I've got a bit of a mirage maker, something that makes a real image. Remember, yesterday we talked about imaginary versus real images, and so we're going to go just take a quick look at a real image. All right, so here we have an example of a mirage of a real image. What looks like here is I have this pig sitting on top of this dome, but that pig is not actually there. If you watch, I can attempt to grab it. It is not actually there. It is a reflected image of the pig that is down there. There he is. This is my actual pig, but when I put him in here and the light comes off him and gets reflected off the spherical mirrors that are here, the concave mirrors. I put the lid back on. There is my pig sitting on top, even though he is not there. So that is just a demonstration of how we can have real images if the mirrors are set up properly. All right, and we're back. So with images, the way we're going to diagram them, there are a couple of rules that you have to follow when we're drawing them. And we're not going to draw a lot of them because drawing is an inexact science. We are rather going to be using the formulas that we'll cover. They're on the board behind me already. We'll cover them in a moment. But the rules are this. Okay, the first rule, and again, write these down if you need to, but you do need to remember these rules. And the rules are this, and the rules are the same for convex or concave mirrors. The first rule says that a ray that is parallel to the principal axis, so any ray that's coming in parallel to the principal axis will get reflected through the focal point. Has to. Okay? So any ray coming from that is parallel to the principal axis will get reflected through the focal point. Okay, so that's rule one. Now let's repeat it one more time because I think I may have said it wrong. A ray that is parallel to the principal axis is reflected through the focal point. All right, rule two is that if we have a ray passing through the focal point, it will get reflected parallel to the principal axis. So it's really just the reverse of the rule. If I have a light ray, and I'll just draw another one here. If I have a light ray, I'll draw it in black. If I have this light ray coming through here this direction, okay, so it's going that way, it will get reflected this way, parallel to the principal axis. So again, the rule, a ray passing through the focal point is reflected parallel to the principal axis. Okay? And then the third rule is simply that if we have a ray that goes through the center of curvature, so if it comes through the center of curvature and hits the mirror, it's going to get reflected straight back. Now, one of the things you have to remember is that all of these rays are still following the law of reflection, which means they are being reflected where theta I equals theta R. Okay? There's a normal line that is right in between these, and we have theta I and theta r, and they will equal. All right, so when we have a ray coming through the center and hitting it, it's following along the diameter, along the radius of the mirror, and it's hitting the mirror perpendicular and then getting reflected straight back through the center. All right, so if it comes through the center, it's going to go back through the center. All right, so those are our three rules. Parallel to the principal axis gets reflected through the focal point. Through the focal point gets reflected parallel to the principal axis. Through the center gets reflected back through the center. All right, then there are two formulas. And again, it's the formulas that are more important because, like I said, drawing is an inexact science. When we do an example on the other board, we will draw it, but you'll see that it's inexact, whereas the formulas will give us numbers that we can actually use and continue working with. So there is something called the mirror equation. And this mirror equation works for plane mirrors, works for convex mirrors, works for concave mirrors. All right, and it is this. 1 over the focal point, focal length, equals 1 over di, which is the image distance, plus 1 over do, which is the object distance. Okay, so this is our formula for all mirrors. It relates the focal length to the image and object distances. And please remember that the distances, remember there's a positive and negative convention, okay? Remember that if it's in front of the mirror, we have positive distances. If it's behind the mirror, we have negative distances. Okay, so when we were doing plane mirrors, our object was in front of the mirror, had a positive distance. The image was behind the mirror, that would be a negative distance. Okay, and so positives and negatives just again tell us where the image is in relation to the mirror and the object. All right, and then with curved mirrors, there's a magnification aspect, and magnification is just a ratio. And so the ratio for magnification, M, is simply HI, which is the image height, divided by HO, which is the object height, which is also going to be equal to the ratio of DI over DO. And again, we're making it negative DI, all right, so that, again, DI could be a negative number, and having a negative out front would then make it positive, divided by DO, all right? And so that's the magnification formula, and obviously in a plane mirror, there's no magnification because HI would equal HO, and DI would equal DO, and so we'd have a magnification of 1, which isn't a magnification at all. All right, but in curved mirrors, these will differ, and we'll get a magnification number. All right, that's a lot of information on one screen. I hope it made some sense. We're going to go and we're going to do an example, and then today you're going to work on some questions that deal with concave mirrors. Tomorrow you'll work on some questions that deal with convex mirrors, and then we'll continue on. All right, let's go do an example. So here's our example. It says a concave mirror has a radius of 20 centimeters. A 2 centimeter tall object is 30 centimeters from the mirror. What is the image position and height? All right, so I've sort of drawn a little bit of a diagram here, and we're going to draw the ray diagram for it right away. But here's my concave mirror. I've drawn my principal axis. I've got a focal point, a center, and my image. The question tells us that the distance from the mirror to the center, the radius, is 20 centimeters. It tells us the object, DO, is 30 centimeters from the mirror. All right, so I've got those two distances here, and it tells us that the height of the object, HO, is 2 centimeters. Now, obviously, this is not to scale because my 2 centimeters is very close to my 20 centimeters. All right, so this is the situation that we have. If I'm going to draw a ray diagram, here's what I'm going to do. I'm going to start by drawing a ray from the tip of my object, and it doesn't matter what the object is, arrows are nice and easy. I'm going to draw it here, and it's going to go to the mirror. So we're going to go parallel to the principal axis. Rays that are parallel to the principal axis get reflected through the focal point. Okay, so it's going that way and that way. Okay, now secondly, we want to draw a ray from the same point that goes through the focal point and gets reflected parallel to the principal axis. So there, and then gets reflected parallel to the principal axis, like so. All right, and you'll see that here I had them intersecting, here I have them intersecting, and if I did this well, if I drew another one that went through the center, pretty close, it would go in and back out, and it would go through that same point. That would tell us that the tip of the arrow is getting reflected here, and if I did all the other points, I would get an image that is in here somewhere. Okay? So from the diagram, we can see that my image is going to be a real image. Okay? It's in front of the mirror, and it looks smaller. But again, drawing is inexact, and we haven't used rulers or to measure the distances or to draw straight lines, but it gives us a pretty good idea of what this might look like. All right, so now let's go and use the formulas now to actually figure out the position and the height of these things. All right, so here we go. We are going to start by finding the focal length. You'll remember from the previous board that focal length equals the radius divided by 2. So we have a radius of 20 centimeters. We're going to divide that by 2. That gives us a focal length of 10 centimeters. And then we'll use our formula 1 over f equals 1 over di plus 1 over do. And we'll fill in our numbers. So 1 over 10. And I'll leave out the units for now, and you can feel free to as well. 1 over di, that's not a 1 over. Let's try 1 over di plus 1 over do, which was 30. All right, so there we go. We're going to subtract the 1/30th from both sides. So we're going to get 1/10 minus 1/30th equals 1 over di. And that will give us, now we're going to figure this out. We're going to use, you guys can use fractions. You guys are good at fractions. Remember, fractions are your friends. Even though we haven't used fractions much in physics, this is an area where you could. Let's get a common denominator. That would make this 3/30ths. 3/30ths minus 1/30th is 2/30ths. 2/30ths is 1 over 15. And if 1 over 15 equals 1 over di, that tells us that di equals to 15 centimeters. And that's pretty close to where we've got it here, right? If f was 10 and c is 20, we're pretty close to right in between there at 15. All right, then we want to find the height. So that's the position. The position is 15 centimeters from the mirror. Now we want to find the height of it, and so we'll do that over here. I'll change colors. Let's do this in black so we can see it. If I want to find the height, we're going to think again of our ratios for magnification, because height depends on magnification. Okay, remember that magnification equals to hi over ho, which equals negative di over do. Okay, any of these three can be true at the same time. So we're just going to forget about the m for a moment here and just use these two ratios, because we now know di, do, and ho, and should be able to find hi from that. So let's plug in our information here. Our hi is what we're looking for, and I'm going to multiply this ho to both sides right off the bat. We're going to get negative di times ho over do. And let's put in our numbers now. We're going to have negative 50 times negative 15. Move this DO up a little bit. And HO was 2. And you'll notice I'm leaving out the units. And again, you can feel free to leave out the units for this case as well. And we're dividing it by DO. And DO was 30. All right. And so negative 15 times 2 is negative 30. And 30 divided by 30 is obviously negative 1. All right, so it says here that the image height is negative 1 centimeters. So the height is 1 centimeter. Now you can't have a negative height. The height is 1 centimeter. The negative is telling us that it is inverted. Okay, so just like positives are on the front side of the mirror while negatives are on the back, for height, positive means it's upright, negative means it's inverted. All right, and it's obviously smaller. We started with a 2 centimeter tall object. We're getting a 1 centimeter image height. All right, so if I'm describing this, some of the questions will ask you to describe the image. Remember the 4 categories we want to describe it. This is a real image, okay, because it's in front of the mirror. It is smaller than the object. It is inverted. And what was the 4th one? I think that's all we need to worry about. Okay, we have it in front of the mirror, so it's real. We have it inverted. We have it smaller. All right, so that's what we want to do when we're describing it. All right, so that's our example. The diagram helps us. The diagram's not going to find us our answers, but it gives us some context for the question, and we can see from our math that our diagram made sense. Okay, so and you can do it either way. The math will always work, right? But it's a good idea to sometimes it's a good idea to know whether you're in the right ballpark, and the diagram will help us know we're in the right ballpark. The diagrams aren't that hard to draw if you remember the 3 rules: parallel, through the focal point, through the focal point, parallel, through the center, back and forth. And then from this, we looked at the formulas. We got our image distance at 15. We got our image height at -1. All right, hope that makes sense. You're going to do a few questions out of your textbook on concave mirrors, and then as I said, tomorrow we'll look at convex mirrors. As always, if you have any questions, let me know, and we will cover them. And again, maybe now before we sign off, I'm going to do the one question that I got from yesterday's assignment, which was question number 10. So we'll go back to the other board and do that question. All right, so with question 10, now chances are, if you had a question on this one, you were probably overthinking a little bit. All right, so question 10 simply says, a car is following another car down a straight road. The first car, the car in the lead, has a rear window tilted at 45 degrees. Draw a ray diagram so that the sun will be reflected into the driver of the second car's face. All right, so here's the window at a 45-degree angle of the lead car. Okay? Here's the person sitting in the trailing car. The light rays from the sun to get reflected here into this guy's eyes are going to, I'll draw it backwards, coming from his eye. If it hits this mirror, okay, there's a normal line, and it is going to get reflected straight up. So from the sun, it's going to come straight down and straight this way into that driver's eyes. And again, we are looking at the property here that theta I has to equal to theta R. And if the mirror is at a 45-degree angle, these angles in there are also going to be 45 degrees each. This ray and the reflected ray are going to be perpendicular. So that's it. You probably overthought it, thinking you had to do more for it, but that's how you do that question. If you have any other questions on the plane mirror assignment or on today's assignment on curved mirrors, let me know. We'll see you tomorrow.